This is a story about a flying telephone pole that redefined the geometry of modern power. When people hear the word Tomahawk, their minds immediately go to a specific cinematic sequence, hundreds of cruise missiles screaming across the dark ocean, turning into lethal streaks of light that paralyze a nation's integrated air defenses and command centers within a matter of hours. This was the reality of 1991. During the Gulf War, the BGM-109 Tomahawk was the signature of asymmetric dominance, a weapon that left global military observers in a state of collective silence. It was the opening act of American global hegemony, the primary tool for non-contact strategic strikes. For over 30 years, whenever the White House wanted to project its resolve without putting a single pilot at risk, the Tomahawk was the first guest to arrive. However, as we stand here today, the script of modern warfare has undergone a subtle yet profound change. As Operation Epic Fury continues to unfold over the Persian Gulf, the scale of Tomahawk expenditure has reached an unprecedented, almost staggering peak. According to data recently disclosed by the Pentagon, within the first month of this conflict alone, the United States has launched over 850 Tomahawks at Iranian military targets. To put that in perspective, that is roughly double the combined total of missiles expended during the 1991 Gulf War, the 1998 Operation Infinite Reach in Sudan and Afghanistan, the 2011 Libya intervention, and the 2017 Syria strike, all added together. Yet despite this massive volume of fire, the sense of an instant knockout has vanished. While the U.S. continues to dismantle high-value targets, we are witnessing more cases of missiles being intercepted by modernized point defense systems, jammed by sophisticated electronic warfare suites, or losing their locks due to sensor overload in contested airspace. It raises a haunting question for strategists. Is the Tomahawk getting old? To answer that, we have to look past the speed and the fireballs and understand the logical evolution of this weapon. In an era obsessed with hypersonic velocity and prompt strike capabilities, why is this slow, subsonic relic from the Cold War still the hardest card in the Pentagon's hand? To understand the Tomahawk, you have to go back to the strategic pain points of the late 1970s. The Soviet Union's integrated air defense system was becoming a dense, impenetrable web. Radars were getting sharper. Surface-to-air missiles were reaching further into contested airspace. For a traditional bomber to hit a target deep in Soviet territory, it had to survive what was essentially a suicide run through layers of interceptors. The US military needed a standoff weapon, a tool that could stay outside the kill zone and deliver a strike from absolute safety. The design brief was simple but brutal. The missile had to be small enough to evade radar, low enough to hide in the terrain, and long-range enough to be launched from thousands of miles away. The result was a cylinder strictly limited to a diameter of 21 inches. This wasn't a random dimension. It was engineered specifically to be compatible with every standard torpedo tube in the US Navy's submarine fleet. This standardization gave the Tomahawk its greatest longevity: universal adaptability. Whether it is launched from a submarine's torpedo tube, a destroyer's vertical launch system, or a mobile ground-based launcher, the firing logic remains identical. Propulsion-wise, the Tomahawk is a marathon runner, not a sprinter. It utilizes a small, remarkably efficient turbofan engine, the Williams International F107 or its modern F412-derived descendants. While these engines only push the missile to a subsonic speed of about Mach 0.74, they are masters of fuel economy. This allows a relatively light missile to achieve an operational range of over 1,600 kilometers. Subsonic flight also offers a critical tactical advantage, a very small infrared signature. Because it doesn't generate the intense friction heat of a supersonic missile, it is far harder for infrared search and track systems to find against the background clutter of the Earth's surface. Furthermore, the Tomahawk survives through its flight profile. By hugging the terrain at altitudes as low as 30 to 50 meters, the missile stays below the radar horizon of long-range batteries. To a radar operator, the missile is often indistinguishable from the noise of the ground. Hills, trees, and buildings act as a physical shield. It doesn't need the expensive, fragile stealth coatings of a B-2 bomber. It uses the Earth itself as a cloak. The surgical reputation of the Tomahawk was built on a redundant composite navigation system that remains a masterpiece of Cold War engineering. Even in 2026, in high-intensity electronic warfare environments where GPS signals are routinely jammed or spoofed, the Tomahawk's physical navigation logic is the ultimate fallback. The first pillar is TERCOM, or terrain contour matching. Think of the missile as a navigator with an incredibly accurate cane. It uses a radar altimeter to sculpt a real-time profile of the ground below and compares it to 3D digital contour maps stored in its onboard computer. It doesn't need satellites, it is entirely autonomous. As long as the mountains and valleys don't move, the missile knows exactly where it is. This allowed the early Tomahawks to navigate across featureless deserts and find their way into the heart of an adversary's territory with terrifying reliability. The second pillar is DSMAC, Digital Scene Matching Area Correlation. This is used for the terminal phase of the flight. As the missile nears the target, an optical sensor takes a photograph of the actual scene and performs a pixel-by-pixel mathematical comparison with pre-stored satellite images. This visual lock ensures that after a 1,000-mile journey, the missile hits its target with decimeter-level precision. In 1991, this was the technology that allowed missiles to turn at intersections and fly through specific ventilation shafts. By the early 1990s, with the Block 3 upgrade, the third pillar, GPS, was integrated. This was a paradigm shift. Before GPS, mission planning was a labor-intensive process that required days of complex topographic mapping and intelligence gathering. GPS shortened this window to minutes, allowing for rapid response strikes. However, the military never abandoned TERCOM or DSMAC. This guidance trinity ensures that if an enemy jams the GPS signal, the missile simply reverts to its internal eyes, reading the ground and the scene to complete its mission. It is a level of resilience that few modern GPS-dependent weapons can match. As the decades passed, the Block 4 tactical Tomahawk introduced the two-way satellite data link. This transformed the missile from a broken kite, a weapon that followed a rigid, unchangeable script, into a sentient online terminal. In the 2026 conflict, commanders receive live sensor feeds from the missile mid-flight, allowing them to assess the target's status before impact. This connectivity allows for loitering, where a missile can circle a target area for up to 2 hours, waiting for the optimal moment to strike, or switching to an entirely different target if the tactical situation changes. In an era where $20,000 suicide drones can take out a main battle tank, has the $2 million subsonic Tomahawk become an expensive dinosaur? If we only look at raw speed, the Tomahawk's Mach 0.74 cruise seems like a slow-motion target for modern air defense. Many observers ask why we no longer see the instant knockout scenarios of the 1991 Gulf War. The answer is found in the Modern Warfare Manual that the US inadvertently wrote for the rest of the world. Since 1991, every major power has studied American precision strikes. They realized that defending a centralized target, a massive headquarters, a fixed radar station, or a dense military camp is a death sentence. Consequently, the logic of defense underwent a revolution: decentralization. In the 2026 Epic Fury conflict, there is no longer a single brain to destroy. Command nodes are fragmented and mobile. Radar units no longer stay active at fixed sites. They operate in shoot-and-scoot cycles. Even communication networks have achieved high levels of redundancy. When an adversary learns to distribute their assets and use cheap jamming equipment to create thousands of ghost targets, the old-school script of a one-night victory officially ends. This is precisely why the role of the Tomahawk has fundamentally shifted from being the finisher to becoming the system-cleaning tool. This tactical shift explains the staggering 850 missile expenditure in the first month of the Iran conflict. The US is no longer attempting to win with a single blow. Instead, it is engaged in a high-intensity, month-long hunt. Because the adversary's nodes are constantly moving, the mission is not about blowing up a building and going home. It is about maintaining a high-density, persistent fire pressure. By flooding the theater with Tomahawks, the US forces these mobile air defense units and command cells to stay in a constant state of retreat and relocation. This unrelenting pressure prevents the decentralized network from ever effectively integrating, allowing the US to dismantle the enemy's nervous system piece by piece. Cheap drones simply cannot perform this task at this scale. While a swarm of drones is effective for short-range harassment, they lack the 1,000-pound kinetic punch and the sophisticated, jam-resistant navigation required to destroy a hardened mobile command center. The Tomahawk is not competing with drones, it is the pioneer that clears the way. It maintains the technical floor of modern industrial warfare, providing a level of destructive certainty that smaller systems cannot match. In this era of massed effects, the Tomahawk's stability ensures it remains the essential opening act for every subsequent wave of military force. While the battlefield proves the Tomahawk's tactical relevance, the back-end industrial reality presents a much colder truth. The 2026 conflict has exposed a brutal mathematical reality: the production ceiling. As we noted, the US has launched 850 Tomahawks in just 1 month. In contrast, the average annual production rate of the American defense industry over the past decade has hovered between 200 and 300 units. 1 month of combat has consumed nearly 3 years of peacetime production. While Raytheon and its suppliers are in an emergency surge to push annual output toward 1,000 units, a Tomahawk is not an easy object to mass produce. It requires specialized turbofan engines, high-temperature composite materials, and advanced microelectronics. Every node in the supply chain, from skilled machinists to rare earth material suppliers, is a potential bottleneck. This inventory anxiety is now a primary driver of American strategic decision-making. Analysts warn that if the US depletes its Tomahawk stockpile in a regional conflict, it may be left vulnerable in a larger peer-level confrontation. This industrial reality tells us that modern war is not just a contest of algorithms and stealth. It is a marathon of production lines. The Tomahawk remains a technological leader, but its long, expensive production cycle is the most fragile link in the American logic of war. When a $2 million missile faces thousands of decentralized targets, the precision strike model faces its ultimate industrial test. In 2026, the winner isn't just the one with the best code, but the one with the most resilient factory floor. The BGM-109 Tomahawk has found a pragmatic new coordinate in the 2026 landscape. It is no longer the knockout punch of the 1990s, but it has evolved into the standard currency of long-range firepower. In a high-intensity conflict, you cannot rely solely on billion-dollar stealth assets or experimental super weapons to solve every problem. You need a reliable, mature, and networked universal fire that can bridge the gap between strategic intent and tactical reality. The endurance of the Tomahawk does not lie in its speed, but in its certainty of strike. Even in environments where GPS is jammed and satellite links are severed, its physical navigation logic, the TERCOM and DSMAC systems that define its DNA, provides a level of performance that newer, more fragile systems lack. This ability to deliver a 1,000-pound warhead to a precise coordinate under almost any condition is what keeps it in the US inventory 40 years after its birth. The 2026 conflict has served as a cold reminder: modern war is an industrial race. When the consumption of missiles is measured in days but production is measured in years, even the most advanced weapon faces the pressure of the inventory red line. This industrial contradiction will dictate the scale and duration of all future conflicts. The Tomahawk, with its blend of stability and precision, defines the practical limit of modern military technology. It is the pioneer that clears the battlefield, the standard that allows the military to maintain pressure, and the hardest card that the Pentagon still holds in its hand. Distance was once a shield for the world's most secluded regimes. The Tomahawk turned that shield into a window. 40 years later, it is still the first to arrive, and it remains the last word in precision.